Hi, my name is Kian. I am doing a SIT 101 1.6 HD test, and I am going to present the topic of clock. And I will be going into more details and discussions for different aspects of clock that was not discussed in the lectures. Also, this is basically an abstraction of the clock we learned. So the clock we learned in the lectures is basically how the clock and clock signal basically interacts with our logic gates. But this, what I'm talking about, is more all the concepts of how the clock is working outside of that. Basically how it works in the whole the computer device and how it comes together, instead of just looking really deep into it with the clock signal or how it works with logic gates together. So uh, let me first give you an overview of the topics we'll be talking today. So this is the overview. So first, I'll be talking about what I currently know from clock, the topic clock from the lectures. I'll go over that. The clock speed, the clock oscillator, RTC, real-time clock, clock drift, how all these topics I talk about come together in a computer device, and then finally the limitations, which I will give an example that I used that I did some research on in my cybersecurity class, and I feel it was appropriate for this to implement this topic. So first, let's talk about what we currently know in the clock form lectures. So let's talk about clock signal. So I'll just give a brief overview of everything we do in the lecture. So we first discussed about the clock signal and how the master clock is dictating the lapse of time, and the master clock has streams of alternative bits and ones. Then we briefly discuss the clock cycle, which is the time of the beginning of the clock. So beginning clock is 0 and the clock is 1. And the clock cycle will be further discussed in my video. I'll build more upon it. The next one. Um, so, so let's talk about the actual gate logic behavior over time. So this explains how the clock is affecting the logic gates over time. As you can see, the physical time right here, it will always move, it continuously always move no matter what. And so while there's no delay in the physical time of the clock, the inputs and outputs will always have delay due to the time that is always moving. So the physical time will always move, it's time. But due to the gate logic, there'll be delays between them. So this basically shows the concept of time and how the clock applies to the logic gates. So the next one, clock cycle design. It's basically the same thing as the stuff before, but this time we'll talk about um, how they give different delays. Uh, and so how the clock cycle gives different delays, which is the propagation delays in the amount of time required for a signal to receive and to be sent. It is caused by the time it takes for the signal to travel through the medium, and a computation delay. Because of the time delays, the clock cycle is put in place to neutralize the time delays. So the cycle length, so it negates the time delay. So it gives time for the output to reach the desired value. So I'm just reading this on. So in this one we talk about combinational logic and sequential logic. So basically, this is more of a digital circuit theory, both of them. And sequential logic is the type of logic circuit where the output depends not only on the present value of its input signals, but on the sequence of past inputs. And it will show the input history in there as well. And this is different from the combinational logic, whose output is the function of only the present input. So now let's talk about clock speed. So now that we're refreshed from what we know on the lectures, uh, we can differentiate it, right? Because the concept I'm explaining is basically different from and build upon the lectures. So I'd like to provide an example. So first, before we talk about clock speed, I'll give an example. Let's say I have an Apple laptop and I turn it on and everything works. Nothing is wrong with it. But on the date when I turn it on, the date of the machine, the laptop, is 1901. So it's running for 121 years behind. So what went wrong here? How does we can think about it, how does the computer actually keep track of time? If you compare it to an actual clock, there's no parts or springs to keep the it's like a clock, but the computer doesn't have that. The computer has different parts. So how does it actually work? Why did my computer not only track the time when it's being kept away, but not every single time we turn it off, right? So so this is clock speed. So let's dissect everything that I just said. So the clock speed of your processor is at a frequency which it operates. The frequency unit is used to indicate that is called hertz. So 1 hertz right here. So 1 cycle per second is represented as 1 hertz. So let's suppose that we have a single core processor with 1 hertz clock speed. It would therefore be able to carry out one instruction every second. So when you consider takes between 1 and 7 cycles, or between 1 and 7 seconds to calculate 2 times 2, it will be really slow. So that's where um that's where clock speed is. So the clock speed of contemporary computers, how it is indicated by multiple gigahertz. So gigahertz, which equals to 1 billion instructions per second. So therefore, you cannot compare two processes with just the clock speed. So right here. So we have two processors, right? We cannot compare both of them, even though you can say that maybe the 2 gigahertz is faster than the 1 gigahertz. With so it has, but really, it depends on the processor's architecture and how many cycles are required to complete a fundamental function. It's possible that the 1 gigahertz, a slower processor, actually need twice as many cycles to perform a multiplication than the 2 gigahertz. So consider a processor that runs at 2 gigahertz right here, which translates to 2 billion instructions per second. We can simply count the number of cycles that have transpired during that process if we want to keep track of time. So we could calculate that half a second that passed, it will count 1 billion cycles. So like between those two, it'll still be equal, right? It just depends on the computer, the device. It doesn't matter. There's a lot of variables, so you can't say which one is faster or not. So really, if you think about it, it's not possible to count every clock cycle. If you try to make a program like a code to kind of count every clock cycle in your computer, um, then there'll be no space to operate other programs. You just be running the clock right there to read every instruction in the computer. Okay, so the next one. So this is a solution. The next one is the topic clock oscillator. I made this myself. So clock oscillator. So therefore, from our last topic, we know all about the clock speed and then how it works. So therefore the computer contains a device known as clock oscillator right here. To make this more effective, this reduces the clock speed to to the speeds that it can run. So such as 1 gigahertz, 100 hertz, or 100 times per second. So the CPU can be interrupted with the help of the slowest signal in order to run a timekeeping software. So this basically says that it's easier to we don't need to run a program. This called oscillator basically does everything for the clock speed, so it can run the processor without having other programs to take up all the space. So the CPU can be interrupted with this help to slow the signal in order to run a timekeeping software, right? So now we know this is a solution. We don't need to run any other programs called oscillators right there. But this gives two more problems. So the first is the accuracy of the clock. So we know this is run from 1 gigahertz to 100 megahertz. This is an example you put, right? So the accuracy of the clock example is basically less. It's less accurate because of the clock oscillator. Because the accuracy in this example is is to be less accurate than 10 milliseconds because we interrupted the CPU 100 times because we slowed it down. So we interrupted it 100 times every 10 milliseconds. So another one is every time we interrupt it to slow it down, we have a lot of power issues. So there's going to be a lot of power loss issues so we need to fix that. So when we turn off the computer, the processor also turns off, right? Even with the clock oscillator, it's still not possible to keep track of time. So what is the solution for this? We run RTC, real-time clock. So RTC is basically in the computer. So computers have this thing called RTC, or real-time clock, to address this final problem that we have just then. This tiny chip, the tiny chip is inside here. This tiny chip is a quartz crystal, and all you need is a really small amount of electricity to pass through to keep track of time, right? It is made to vibrate at a particular frequency that brings up the hertz. It depends, it depends on electricity, it depends on a lot of variables, but this is basically just a simple diagram. Additionally, you can keep track of time by counting these vibrations because the quartz is like really small and it's really affordable, and it uses very little power, and it's very accurate, and it's frequently used in timepieces. So a tiny battery within a new computer powers the RTC. So the battery provides electricity and it goes to the RTC and it counts the time. It keeps it operational. So basically my previous laptop, so like the example I gave the first one, inability to keep track of time was because the RTC, the battery or the quartz was basically dying. And this is obviously to be expected. Over the years, it's gonna, it's just gonna get old, and then it might just come off. So when a system started up, it was unable to read the time or the RTC, and it defaults the time to 1970. That I made the example, which was the time that I closed it. Yeah, this is just an example, right? But RTC is not in just computers; it's also in laptops and smartphones. They're just small and they're just quartz. Yeah. So modern electricity that I talked about, smartphones and laptops use small RTC. In fact, it would be difficult to detect. So we can turn off our computers without worrying that they won't remember our time with the real-time clock right here. And when we turn them back on because RTC. However, an RTC isn't always correct. Like really, it has the ability to gain and lose time as much as 15 seconds every 30 days. So whenever you use it over a long period of time, it may either run ahead or behind schedule of the current time. So we need to occasionally like adjust the time to make sure that it doesn't either go ahead or go behind. So now we know that RTC is a solution, but it's not the perfect solution. So what can we build upon it? We use clock drift. So this is a diagram between using a computer connected to the atomic clock at the end here. So the fact that the clock's position is restricted with the RTC is what causes between going behind or after the time, which is known as clock drift. Uh, but the modern computers that we have can make up for this. So the modern computers we have can use a network time protocol to synchronize this clock with a precise source, like the atomic clock. So when it is linked to the internet, so this computer is the internet, this computer is the internet, this is the atomic clock. So when it's linked to the internet, it can use the atomic clock. Even with internet delay, speed ups can be made up via NTP. It is actually accurate within a few tens of milliseconds over the open internet. However, it can be lowered to less than 1 millisecond on local networks. Okay, so we discuss clock. So we discussed all these topics. So now let's put it together. So let's think. Okay. So first, so how does it come together? So first, the operating system will retrieve the time from the RTC. So the system will go here. The system time will retrieve from the RTC. And when you power on your device, because it has been tracking while it was turned off, by halting the process at these regular intervals, the operating system will now maintain a time separately. To account for any clock drift, it will synchronize its time with the NCP on a regular basis. So finally, the RTC will keep track of time, and even after you turn off your computer, the system boot go to OS will fetch a time to RTC. It will sync up with NTP right here. Assuming you shut down your computer, right? You go RTC will continue to keep track of time, and then it will go to system boot, and it will start the cycle over again. So this one, you will never lose track of time because of all these aspects and variables that we discussed. So let's look at the limitations. This is a problem where I noticed I think it was a task in cybersecurity about the Linux 2038 issue, and I felt that this was very appropriate to put this in here because it was to do with clock and it was to do with time, typically how Linux set the time. So now we understand everything that we talked about, all the aspects and how a computer tracks time. But is it possible they can do everything indefinitely? There is some restrictions, right? Like here I said limitations. So one of them is the Linux 2038 issue that impacts Linux computers. So they use the number of seconds that have lapsed since January 1930. In January 1930 here, 1901, sorry, 1901, to represent time to save that information as a signed integer. So what happened was they set it as 1901, and this is the illustration that I'm going to show you. So the 0 right here in this case, it denotes a positive value. So the counter will go up on negative January 19, 2038. So when it hits January 19, 2038, all the binary come here, it'll increase by 1, right? Each day. After that, it'll go negative. And then it will turn to this, and then it will just go back to 1901. But this is basically a bug, and mostly 64-bit operating systems, it won't affect it. But for old devices, like outdated legacy systems, that is difficult to change anything inside of it, that will be an issue. But probably in the future they'll have a fix for it, but this is a limitation that we can talk about. And that is it. That is my HT task talking about clock. Thank you.